In this video, we start up with the calculus of inverse functions. Like, is it possible to differentiate or integrate inverse functions? First of all, we start with the differentiation. And now to begin, we want to state two important theorems that if f is a one-to-one continuous function defined on an interval, say I, then its inverse function is also continuous. Now, if f is a one-to-one differentiable function with inverse, f inverse, and the derivative of f composed with f inverse at a point A is non-zero, then the inverse is differentiable at that point A, and its derivative is defined as f inverse prime of A is equal to 1 over f prime of f inverse of A. And the proof of this theorem is in the text if you want to look it up, but we're not concerned with the proof here. We just want to see how to use this formula, and these examples makes the use clear. Now let's consider the first example. We are asked to compute the derivative of at the points indicated of the function given. The first one, we are asked to compute f inverse prime of 1, that is the derivative of f inverse at 1, where f is defined to be x squared. And now x squared is not really one-to-one in the whole of R. However, as we said earlier, if we can restrict the domain of f inverse, we can get the part that is one-to-one that has an inverse. And that is why in this case we restricted the domain to be x contained in 0 in the interval 0, 2. And now if you look at this graphically, this curve, the graph of this function looks like this. It looks like this, and then this place is from 0 to this point, maybe 2. And if you check, this passes the horizontal line test, so it's invertible. Now we can compute the inverse of the derivative of this inverse at the point 1. To do that, we want to use the formula that we stated above here. So we are looking for f inverse prime of 1, and that is replacing A in the formula with 1. That would be 1 over f prime of f inverse of 1. So here, to compute this, we need f prime and we need f inverse of 1. So it's easy for this function that is given. Let's write that right here. If f of x is equal to x squared, and then my f inverse of x is equal to the square root of x. You can verify this. Now my f inverse of 1 would just be the square root of 1, which is equal to 1. Now what is my f prime? So I'm looking for f prime now. F prime will be 2x. So let's come around here. We found that my f inverse of 1 is 1. So this formula reduces if we replace this with its value. Then we have that this will be 1 over f prime of f inverse of 1 is 1. So I'm just going to have 1 here. So if my f of x is equal to 2x, or f prime of x is equal to 2x, that means my f prime of 1 is just going to be 2. So this formula becomes 1 over 2. Now, if you check, this is actually consistent with the derivative of the inverse function if we define it to be x squared. Recall that we say that f inverse of x is equal to square root of x. And now f inverse of the derivative of f inverse of x, if I'm going to write that in blue, would be f inverse of x. If we differentiate that, the derivative here of x, differentiating square root of x gives me 1 over 2 root x. So that tells me that my f inverse or prime of 1 is going to be 1 over 2 square root of 1, which is the same thing as 1 over 2. So anyway you get this done, you still get the same thing. So the formula becomes very important when it's difficult for us to find the inverse of the function explicitly, as we did it in this, as the next example shows. So now we move to example 2. I'll have to put a box around this. So let's move to example 2. We are asked to find the derivative of the inverse function at 1 when the function is given as 2x plus cosine of x. You agree with me that it will be difficult for you to find the inverse of this function explicitly. But how can you find the derivative at the point that is indicated? Now, this is the way we do this. First of all, we want to write out the formula, and the formula says that f inverse prime of 1 is equal to 1 over f prime of f inverse of 1. So now we need f inverse of 1. I'm going to do that here. I know that my f of x by definition is equal to 2x plus cosine of x. However, how do I get my f inverse of 1? Well, notice here that my f of 0 is equal to 2 times 0, which is 0, plus cosine of 0, which is 1. That tells me that my f of 0 is equal to 1. So therefore, my f inverse of 1 would be equal to 0 by definition of inverse function. So we got this by observation. Many of the problems you encounter, you have to make the observation of how to find the inverse of a given function at a particular point. So we found that f inverse of 1 is equal to 0. The next thing we need is f prime at this point. So my f prime of x, differentiating f of x, is going to be 2 minus sine of x. And my f prime of 0 will just be equal to 2 because sine of 0 is 0. So if I plug in the values back into the formula, I get 1 over f prime of f inverse of 1 is 0. And this will be equal to f prime of 0 is 2. So I'm going to have 1 over 2 as the final answer. So for the function given, the derivative of the inverse function at 1 is 1/2. It's kind of like a coincidence for the first and second examples to have the same solution. Now we try to solve this one also, or employ the same method for example 3. Similarly, we go with the formula, and the formula says that f inverse prime of 5 is equal to 1 over f prime f inverse of 5. So here we need f inverse of 5. How do we get that? Well, we could do it somewhere. I know by definition that I was given that f of x is equal to 3x cubed plus 4x, or 4x squared please, plus 6x plus 5. Now, for me to be able to find out what my f inverse of 5 is, I'm going to ask myself, What value of x is going to give me 5 for this function? What I mean is this: is there any value a such that f of a is equal to 5? If any such value exists, that means that my f inverse of 5 is equal to a. Now clearly, from observation, you see that if you plug in the value 0 for x in this function that is given, you're going to get 5. So that means my f of 0 is equal to 5. So I'll write that here. F of 0 will be 3 times 0 plus 4 times 0 plus 6 times 0 is equal to 5. That tells me that my f inverse of 5 is equal to 0. The next thing we need to do is to find the derivative of f of x. So we find that f prime of x would be 9x squared plus 4x, this should be 8x plus 6. And f prime of 0 would be 6. So now we have f prime and we have f inverse. We now substitute the values inside the formula. So doing that gives me 1 over f prime of f inverse of 5 is 0. So I'm going to have 0 here. And the last substitution I'm going to make is f prime of 0, which is 6. That tells me that in conclusion, that my f inverse prime of 5 for the function defined above is 1 over 6. Now we can apply this formula to solve problems in this form. However, we also say that a function can be defined by a graph. And if the graph is 1-to-1, is it also possible for us to find the derivative of that function defined by a graph at a particular point? Well, we'll see how we can do that in the next video.